Deep learning is a part of artificial intelligence that uses advanced neural networks with lots of layers to tackle complex problems. It's like how our brains work to process information. These networks help machines recognize patterns, make decisions, and learn from the data they get. Neural networks are the building blocks of deep learning. They consist of layers of connected nodes, or neurons, that pass along information. Each layer takes the input data and makes it more abstract, which helps the network figure out really intricate patterns. There are three widely used types of neural networks for deep learning: artificial neural network, or ANN, convolutional neural network, or CNN, and recurrent neural network, or RNN. ANNs are computing systems inspired by biological neural networks. They are designed to recognize patterns, interpret data, and make decisions by simulating the way human brains process information. ANNs consist of interconnected layers of nodes, which are also known as neurons. Each node performs a simple computation and passes the result to subsequent layers. An ANN typically contains an input layer, a number of hidden layers, and an output layer. Each node in a layer is connected to every node in the adjacent layers. During training, data starts by entering the input layer. Each node functions as a processing unit, as illustrated in the figure, which shows the inputs X, weights W, bias B, and activation function F. The node computes a weighted sum of its inputs, adds a bias, and then applies an activation function to introduce nonlinearity. The result is then passed to the next layer. The data then moves through several hidden layers where the same processing happens, and finally it reaches the output layer where the network makes a prediction. Once we have the output, we compare it to the ground truth or the actual values using a loss function. This function measures the prediction error, or how far off the network's predictions are from the real answers. Here is an example where mean squared error is used as a loss function to measure the error between the prediction y and the ground truth y hat. We then use this error to adjust the weights and the biases of the neurons through a process called backpropagation. This process typically uses gradient descent or similar optimization techniques. The training process involves running many cycles called epochs over the training data to gradually improve the network's accuracy by minimizing the error. After training, the neural network can be used to make predictions. Convolutional neural networks are a type of deep neural network designed for handling structured grid data, such as images. They are really good at recognizing patterns, shapes, and structures in images. This makes them perfect for tasks such as image recognition and object detection. A typical CNN consists of three main types of layers: convolutional layers, pooling layers, and fully connected layers. The convolutional layers apply filters to the input data to generate feature maps, detecting important features such as edges and textures. Pooling layers then reduce the size of these feature maps, cutting down on the computational load and the number of parameters in the network. They do this by methods such as max pooling, which retains key features, or average pooling, which reduces noise. Fully connected layers work similarly to those in traditional neural networks, where each neuron connects to every neuron in the previous layer. These layers are usually at the end of the network. They make decisions based on the features identified by the convolutional and pooling layers. During operation, an input image moves through the network's convolutional layers. Each layer applies multiple filters to create feature maps. After each convolution, an activation function, such as ReLU, introduces nonlinearity, helping the network learn more intricate patterns. Following this, pooling layers downsample the feature maps, keeping crucial information while controlling complexity and preventing overfitting. After several rounds of convolution and pooling, the resulting data is flattened into a single vector and processed by fully connected layers for tasks such as classification or regression. The final layer produces the network's output, such as probabilities for different classes in classification. To train, we compare the network's output to actual values using a loss function that measures the error. This error is then used in backpropagation, adjusting the weights of the filters and the weights in the fully connected layers to minimize errors using optimization techniques such as gradient descent. RNNs are designed to work with sequences of data, such as time series information or natural language. Unlike traditional feed-forward neural networks, which process data from start to finish, RNNs have connections that loop back on themselves. This unique feature allows RNNs to remember information from previous steps in the sequence, making them ideal for tasks where the order of the data is important. An RNN has three main layers: the input layer, the recurrent layer, and the output layer. The recurrent layer is where the magic happens. It has neurons that not only process the current data, but also keep a memory of previous data points through connections that loop back to themselves. This setup helps the network keep track of information over time. When an RNN is working, it processes data one step at a time. At each step, it takes the current data point and combines it with the memory from the previous step. This way, it can build up a short-term memory of the sequence. This figure illustrates how the current data point xt and the state of the previous time step ht-1 together influence the output ot. To train an RNN, we use a method called backpropagation through time. In this method, we unroll the sequence like a series of steps in a chain, treating each step as a layer in a standard feed-forward network. We calculate errors at each step and then work backwards through this chain to update the network's weights and biases to reduce errors. One challenge with standard RNNs is that they can struggle with long sequences due to issues such as vanishing or exploding gradients. To handle these problems, More advanced RNNs, such as long short-term memory networks and gated recurrent unit networks, have been developed. These advanced models include special mechanisms to better manage long-range dependencies.